I'm going to carry on right where Nick left off. We published a paper with myself and Suzanne Dufour, who's in the audience here, recently, suggesting that the rangy morphs, particularly some of these reclining types like Fractifusus that we've already heard about, actually were pre-placozoan diploblasts, and I'll explain some of the reasoning for that. So this story has been developing partly through the Oxford MUN group for some time. And I'd like to just start with the Ives-Hediomorphs, which many of you will see on the field trips. Some years ago now, in 2011, Alex Liu, myself and Martin Brazier suggested that these large irregular blobs on the seafloor that were being preserved with like little triangle shapes and things in it were actually necromass. So that's the remains of dead things on the seafloor. We'd known them from the UK for a long time. They had Latin binomials. The genus names were Ives-Hedia, Blackbrookia, and Shepshedia. But basically, they were so poorly defined, there's no internal shape to them. And what Alex discovered through his early research with Martin and I was that you could take a gradation from really beautifully preserved things like the Fractifusus that you'd see on the front of a textbook, and you can grade to something that's basically a pile of mush. And the advantage with the Ediacaran is that instead of this just dissolving into nothing, we get to actually preserve the piles of mush every now and again underneath tufts. The Ives-Hediomorphs have been part of the story that we've been developing for some time now. Like Martin Brazier started developing this with me, well, actually independently, and we both converged on the same conclusion. One of the interesting things about the Ives-Hediomorphs is that they are commonly associated with the Fractifusus. So the Fractifusus are reclining organisms. I think most of the Ediacaran people here will agree with that. One of the bizarre things about it is that Fractifusus is one of the few taxa that will actually overlie another taxon. In these assemblages, we see them scattered all over the place, but if you see one thing on top of another, it's invariably a Fractifusus. There are some exceptions to that, but the vast majority of them are Fractifusus. I don't know how many of you have been to the beach and turned over stones and bits of wood, but if you do so, you often see that there's a black layer underneath. And that black layer gives off a nasty sulfurous smell, and the reason for that is that it has a superabundance of hydrogen sulfide. There's probably some methane mixed in there as well. So things that were lying on top of dead things, dead and decomposing things, were almost undoubtedly experiencing high levels of hydrogen sulfide, carbon dioxide, and maybe even methane. And this led us to think, well, what were they doing? How did they cope with that? Because hydrogen sulfide, as I think you will all know, is extremely toxic. So there are many, many examples of this, and so you can see here there's a frondose taxon here, which has a Fractifusus growing over the top of it. And the relationships are very clear. You can zoom right in, you can see that the Fractifusus is actually overprinting the morphology of the frondose taxon. And Fractifusus isn't alone. In the paper that we published last year, we were quite deliberately slightly vague about which rangy-morphs we were talking about because we don't yet know. But there are many taxa that have the potential at least to have grown on the surface. Nick talked about these things being up in the water column and exploiting currents. Actually, that's an inference in many cases. They might work just as well laying on the seafloor and interacting with the seafloor, as I think I'll explain, hopefully convincingly, in the next few minutes. So if you're lying on the seafloor, basically what you're doing is you're forming a barrier between the sediment and the water column above. And what will happen is that hydrogen sulfide, toxic hydrogen sulfide, will build up underneath your body. So there's various ways you can go about avoiding that. Things like the sea anemones that we were talking about just there. They secrete a barrier of mucus. This is one from the Bombay Marine Station that some of the guys saw last week. This is a Cereanthid anemone, and it has a layer of mucus which you can actually see is actually harboring some of these sulfurous bacteria on the surface. The other thing that you can do is you can move. And again, the sea anemones evolved that fairly early with their hydrostatic skeleton. And they wandered around on the seafloor, and we can actually see their trails. And we used Metridium as an example taxon for how you might produce push trails in the Ediacaran. So this is from Mistaken Point, again published by Liu et al. So one of the other possibilities would be to decrease the surface area that's in contact with the sediment. And again, Nick preempted me with a lot of the discussion there about surface area. If you were to be lying on the sea floor and underneath you is an increasing amount of hydrogen sulfide, the last thing you would want to do in most cases would be to increase your surface area in a fractal way. So the fractals increase the surface area enormously. So for us, the lower surface of the fractifusus is telling us something quite profound. This thing didn't care about the hydrogen sulfide underneath its body. If anything, it seemed to be welcoming it. Hydrogen sulfide is obviously everywhere. The water column is full of sulfate. All you've got to do is have a little bit of organic matter and you start reducing it and you produce hydrogen sulfide. In some places it's going to be higher than others. So for example, on top of those Ives morphs we talked about, there might be very high concentrations. And it would seem that maybe fractifusus is a tolerator of those kinds of conditions. They're not just found on top of the Ives morphs, I should add. So in wondering what they were doing with this hydrogen sulfide, I collaborated with my colleague Suzanne Dufour about 5 or 6 years ago now. Suzanne works on thiacirid clams, which have sulfur symbionts. So the thiacirid, I don't know if you can see the shell there actually. What you're looking at is the gill, and there's the shell comes around here. The thiacirids actually pump hydrogen sulfide from the sediment towards the gills where they harbor chemoautotrophic bacteria. So they would be thiotrophs that are eating the sulfur, getting energy from the sulfur. So they oxidize it as an energy source and they grow, and periodically the bacteria are ingested through the gills, through that high surface area tissue, into the body as food for the thiacirid. So in the same way, in lots of regards, as fractifusus is having a high surface area in contact with hydrogen sulfide, we would say that the thiacirid clams are doing exactly the same. They're transporting the hydrogen sulfide to their highest surface area part of their body. But as I said, hydrogen sulfide is toxic to cells. And so in order for them to live, they must have employed some sort of tactic similar to the thiacirids to oxidize the hydrogen sulfide before it got to their body, their tissues, and destroyed the cells themselves. It actually causes cell death. So one possibility is that they had a ciliated outer surface, so surface covered with flagellae that would waft water underneath their bodies to constantly supply oxygen, which would oxidize the hydrogen sulfide as food for the thiotrophic bacteria. The other possibility is that it could diffuse through the mesenchyme, so through the body tissues, the glutinous bit that you find in a jellyfish, for example. And interestingly, when we probed into the literature of the Scyphomedusae, actually they use their mesenchyme as a source, as a place to store oxygen during low oxygen periods of time. So that may be something that the orangomorphs were capable of if they were indeed diploblasts, as we propose. And again, as Nick preempted in his talk, this diploblastic tissue arrangement means that basically most of your body is jelly. And there's only needs to be a thin layer of cells around the outside. And so you can grow very, very large very quickly, because all you've got to do is increase that one layer of cells on the outside, and you can spread out over increasingly large areas of the seafloor to effectively get your hydrogen sulfide for food for your symbionts. And that may help explain one of the phenomena that Guy Narbonne highlighted in his paper, I think in 2005-ish, in that life got big, and when life started out, the first fossils that we get, these rangiomorphs, are enormous, absolutely enormous. You put them next to the small shelly fossils, and they dwarf them. And how did they do that? Well, this is a potential solution, just to have them grow much like jellyfish, and just having that single outer layer, which was supplied with oxygen by cilia. So if an organism is supplying oxygen to its lower surface, what it's doing in effect is the same as lots of trace fossils doing. There's lots of trace fossil people in the room here. There are many, many open burrows in which organisms pump water through the burrow in order to farm bacteria on the surface. Now, most things like worms, they actually feed on them in terms of actually grazing on them with mandibles, etc., or maybe with tentacles if they were cnidarians. But the other possibility is that the biota that was naturally growing on the undersurface of these rangiomorphs could actually be phagocytosed. It could actually be ingested into vacuoles into the body as a source of food. Now, we're not sure whether that's a passive thing, whether the main concern originally for these rangiomorphs was just not dying on their lower surfaces because of all this hydrogen sulfide, and passively incorporated this phagocytotic mode of life, or maybe they actually encouraged those microbes and actually cultured them on their body tissues. So then the higher the surface area, the more fractal the lower surface area, the more microbes you can grow, the more food you're going to get. The other possibility is that you could actually pump the hydrogen sulfide in through the tissues and use a trophosome, as some of the flatworms do, which is basically the same sort of jelly-like tissue, but actually the symbionts would be inside the body tissue. So it seemed to us anyway that by far the most simple solution to being particularly a reclining rangiomorph would be to be a diploblast, so to just have a jelly-like central area, which could be a buffer between you and the seawater, or it could be a store of oxygen. And on your lower surface, make use of the natural microbiota that builds up underneath an impermeable surface. So that would be the thiotrophs and the methanotrophs that would naturally accumulate there, particularly if you can pump oxygen to that lower surface. The most simple modern organisms that we have are the placozoans, and Nick highlighted the placozoa as being osmotrophic organisms, so they actually put out those exoenzymes into the environment and suck up the soup, if you like. This would seem to be a mode of life that's a little bit more efficient than that, in that you don't have to waste the energy on the enzymes. It's much more simple in that you don't have to have evolved exoenzymes. So we think that this is maybe a slightly more primitive mode of life for a metazoan than being a placozoan. And that would fit with the stratigraphic position of these reclining rangiomorphs right down in the lowest of the rocks that we have with macrofossils in. So the rangiomorphs encounter some problems because they were immotile. They can't move. Nick highlighted the sea anemones again. But the sea anemones can wander off. They can leave traces. And as I think the majority of the Ediacaran people will know, traces associated directly with any of the rangiomorphs are nearly non-existent, if existent at all. There are some slight adjustment traces, but not with things that we know would have the complex frond-like morphology, for example. So we suggest that they probably gain nutrition from a combination of phagotrophy and symbiosis with chemolithoautotrophs. But then what about the frondose taxa? And one of the things that we've been wrestling with, and I don't have an answer to it yet, I need to spend some more time at it, is many of the people who've worked on the frondose things have put them up in the water column. And if you remember the first image that I showed with the fossils on the bedding plane, there's no real reason why they couldn't be growing along the bedding plane. So basically the stalk would then be a means to get away from the origin, from the holdfast, for example. And the frond, maybe it was an oxygen collecting organ that could be raised and lowered onto the seafloor. So it would serve, in the case of something like Arangia, for example, it would serve dual purpose. It could actually collect oxygen, as we heard before, but it could also be laid down on the seafloor periodically so that hydrogen sulfide could build up underneath to feed symbionts associated with the high surface area, the fractal surface area of the rangiomorph itself. Now, in terms of finding some evidence for that, there's very, very little evidence anywhere amongst the rangiomorphs for them having been swishing around on the seafloor. They seem to be, if you look at them, really rather fixed. You don't see evidence, even in these turbidity currents, you don't see much evidence for them swaying from side to side, producing Kalinga-type morphologies. Mostly they seem to have stuck fairly soundly to where they were. One exception to that is a specimen, in my opinion, I know Alex disagrees, down at Mistaken Point, which we originally described as looping tracers from these features in here. But with the model that we developed, it could be that these are actually the frond laying itself down on the seafloor and being adjusted by the organism itself in order to capture the hydrogen sulfide to feed its symbionts. And there is a modern analog for that. The tiny ciliate Zoothamian does the same. It lives in eelgrass beds. It lowers itself down. It builds up the sulfur levels, raises itself up to get oxygen repeatedly. So just in conclusion, just to summarize, the hydrogen sulfide toxicity problem is something that anybody who's dealing with the rangiomorphs, the reclining rangiomorphs, needs to address. If you're immotile on the seafloor, there's nothing you can do. Hydrogen sulfide is going to build up unless you're going to pump oxygen to that lower surface. Rangiomorphs had a high surface area in contact with the seafloor, and we think that that's because it actually was encouraging that hydrogen sulfide. It must have been pumping oxygen down to that surface. And the logical extension of that is that there would have been increased microbial productivity that could just be phagocytosed. The materials could be absorbed into the body of the rangiomorph. The frondose forms may have been able to lay down and raise up. I don't know. I'm just putting that out there. But it's something that needs to be investigated, and particularly people need to think a bit more carefully about the frondose things as to why they weren't swishing about on the seafloor, as most things probably would do in a current. So I'm not ruling out osmotrophy. Osmotrophy almost undoubtedly happened. But particularly in these very early forms, I think there's something really significant about the fact that they couldn't move, they had a problem, and that problem also solves the feeding problem that we've been talking about for a very long time. Thank you very much.